What I'm supposed to talk about. I did prepare something, however.
Okay. Is this an exam? And is it a compulsory talk?
I don't, it's not a compulsory talk, and I don't give exams in my classes. Yeah. So you're safe. Relax. It's terrible, isn't it? Yeah, it's terrible. Okay, I wanted to say a little bit about this parabolic induction, which was mentioned, because it has a dynamical flavor. This whole subject has a dynamical flavor, which makes me think just a little bit about Farrell and Jones. And so I just offer a few remarks about dynamics and parabolic subgroups as a suggestion to Arthur, and then over to you. Then you can do something with it. Okay, so let's assume not too much. Let's talk about just this one group. I didn't mention it the last time I talked, but a lot of what goes on in representation theory depends on understanding not just this commutative polynomial algebra that I was talking about, the center of the enveloping algebra, but also the maximal compact subgroup inside of G. So that plays a big role, which I suppressed last time. It's mostly going to be suppressed here, but for setting the stage for one other group. This is how all these talks start, by the way. It's like the Eskimos and the polar bears and so on. Every single part of the alphabet is used by the representation theorists. There's not a letter which isn't referring to some subgroup. I'm sure you've all had this experience. You go to one of these talks, damn, it just goes on and on and on. And by the time they're finished with the notation, you're already lost and they haven't really started. Anyway, here's what A is. It's just the diagonal, positive diagonal matrices. All the entries are positive. Of determinant 1, of course, if we're talking about SLNR. So it's a fact that G, everything in G, can be written as K times A times A, K. That's pretty easy to see. That's just linear algebra, spectral theory, diagonalization, and so on. Okay. So this A, if you like, gives the collection of directions towards infinity. In the group G. G looks like two compact things, but the essentially non-compact part of G is just a vector space, A. I mean, A, when you take the logarithms, A just looks like a vector space. Okay, you could do a little bit better. There's a Weil group floating around. There are several Weil groups in this theory, and to keep the outsiders out, they're all called the same thing, so you never know which one they're talking about. You can look at those things in K which conjugate A to itself, and those things in K which actually commute with A. Here it's just the plus or minus 1 matrices down the diagonal, and this thing is the Weil group. It's just a group of all permutations of the entries of A in this particular case. Okay. And a fundamental domain for the conjugation action of A, of W on A, would be the set of diagonal matrices with, for example, take your pick, let's do it this way, with the A's non-increasing like that. That's a fundamental domain. So this sort of condition that we saw last time of dominance is related to the hidden role of some Weil group. Okay. Now, what are these parabolic subgroups about? Let's devote a whole beautiful fresh board to them. I want to fix, there's lots of parabolic subgroups, not continuously many or anything like that. There's a few of them. And they depend on a choice of one parameter subgroup that you can fit inside of A. So you could look at such a homomorphism as this. We could take the exponential of t times some alpha 1, exponential t times some alpha n. So this is some one parameter group. In A, otherwise known as an element of the Lie algebra of A. And now we build some groups according to the following definition. I forgot to say, let me just stick it up here. The best place to read about these things, in my opinion, is an unexpected source. It's the lecture notes of Joseph Bernstein from about 1992 on representations of, and this is what makes it a little bit surprising, p-adic groups. So we're not talking about p-adic groups, but what Joseph Bernstein says in these notes is by far the most accessible introduction to the basic ideas of representation theory, which are, roughly speaking, the same for p-adic groups and real groups. So I really recommend these notes. These are just the most wonderful thing to read if you're interested in representation theory. All right, so here's a one-parameter group. And now let me do the following thing. Let me define an N to be the set of elements in G. It's a subgroup of G, and it's just the elements. Oopsie. It's just the elements which are shrunk to the identity by this one-parameter group as it acts under conjugation. I forgot that I'd given it a name, alpha. It makes a difference which way t goes, but let's say t goes to plus infinity, like that. This is called the unipotent subgroup associated to alpha, and there's also an L, Levy factor, which is just the centralizer of this one-parameter group. So it's just a set of all G's which don't go anywhere under this action. It wouldn't be fair, would it, if we just kept it at these two guys? We should certainly stick in another one. It's called the opposite unipotent. And it's defined like n, except t goes in the other direction, to minus infinity. And if you're looking at A's, one-parameter groups which correspond to alphas which are, let's say, increasing or non-decreasing, then it's easy to see that this n is just a bunch of upper triangular matrices with ones on the diagonal, and this L is a bunch of block diagonal matrices, and exactly how n and L look depends on whether there are coincidences among the alphas. If all of the alphas are distinct, if it's just a generic situation in which all of the alphas are distinct, so alpha 1 is strictly less than alpha 2 and so on, then in that situation, this is exactly the upper triangular matrices with ones on the diagonal, and this is the diagonal matrices. But in general, we're talking about block diagonal matrices down here, and we're looking at block unipotent upper triangular matrices here. It's really easy. And there's this interesting dynamical flavor to it, which is part of all of representation theory. You go back after you've read Bernstein's notes, and you look at what Harish-Chandra did. All of a sudden it makes sense. You know, it makes much more sense with a little bit of geometry there. Of course, if you're tough like Harish-Chandra, you don't need geometry. You know, you don't. That's for sissies. That's stuff. Okay. So now let me tell you what a parabolically induced representation is, what parabolic induction is. It's just a funny thing. You know, it doesn't look like it's an object of particular importance. It only assumes some importance when you look at related operations. There's something called parabolic restriction, which I'll tell you about too. And that's much more closely related to this dynamical business. But we'll start with induction. So let's fix an alpha, and let's fix, therefore, an n and an L. Oh, I forgot one key piece of information. I'll stick it here, which is what is a parabolic subgroup. It's just the product of L times n. L normalizes n, so the product is a group in its own right. So when you do parabolic induction, it's a way of taking representations of L and making them into representations of G, but you use the P as a vehicle in the following way. I'll write this in terms of spaces. Suppose V is a vector space on which the group L acts by a representation pi. Maybe I should write that down. Then you can build a new space consisting of functions on G. This is what people do. This is what induction is generally speaking all about. And then there's some twisted periodicity condition. And for this type of induction, it looks like this. If you have f of GL, this is just pi of L inverse times f of G. And the n gets forgotten. That's the way it is. Okay. Okay. So from the point of view of algebras and modules, as I was talking about yesterday, you could think of it in the following way. You could take the space, which is the homogeneous space G modulo n, it's often called the basic affine space, the affine space associated to alpha, and you could take some good class of functions on it, for example, some exponentially decaying functions S of G mod n, and then you can consider this as a bimodule. Let's just think about it. So L acts on this homogeneous space on the right because L normalizes n. So it makes sense to right multiply a coset, a left coset by L. On the other hand, of course, it makes sense to left multiply a left coset by G. So this thing is a GL bimodule, and so I can form this tensor product. And that's what we're talking about here. Okay. Or if we're talking about
I think I got lost in the definition of the induction. So it's f of GL.
f of, hang on, what? F here?
Yeah.
So f of any group element G times any element of L, the group L, times any n is given by this formula. So n does not enter into the picture at all.
So
why does n go away? Yeah. So what I'm doing in the language of ordinary induction is I'm starting with this representation. I'm using the fact that P has L is a quotient of P, like this. You just forget the n factor. So I'm taking any representation of L, I'm making it a representation of P, and then I'm inducing in the ordinary way. There's a little nuance here which I'm just ignoring. There's some, as they say, row shift, which it's not necessary for us to talk about. So I will lie by suppressing a small piece of information. You need to talk about half. If you're French, it's no problem. I need to be talking about half densities, not functions. But if you're not French, then half densities don't mean anything to you. So, okay. Anyway, here, in the context of tempered representations, you can do exactly the same thing. And there's a compatibility between these two operations. I won't go into it. All right. It's really hard to love this definition by itself because, I mean, it was discovered experimentally that these representations are interesting and they constitute most of the representations of SLN. Most of the representations of SLN come in exactly this way. In fact, they all come in this way if n is bigger than 2, from simpler representations of block diagonal subgroups. So obviously it's an important, experimentally, we see it's an important construction. But why it's important, that we don't understand yet. I mean, in this little talk, we don't understand it. So let's try and make it seem a little more reasonable. So that has to do with this dynamics business. Which you can read about in Bernstein's notes, and nowhere else. Nobody else mentions this. Okay. So there's an operation which you might call parabolic restriction. In the books, they don't call it this. This is what people call, they just call it the exponents, but if you like, the modulo of exponents. Pretty easy. If I have a representation of G, I can bring it down to a representation, like a perhaps I should be consistent in my notation. This is going to be a representation of L, not of P, despite the strange notation here. And it's much easier to explain what it is in terms of this tensor product notation. I'll just look at the, instead of left cosets, I'll look at right cosets. Why not? Okay. So I get a representation of the diagonal subgroup, this block diagonal subgroup here, out of a representation of G. And there's a theorem, not of Frobenius, but there's a Frobenius reciprocity theorem here, which says that this thing here, restriction, is adjoint, left adjoint. Goes hand in hand. If you don't like adjoints, it just means it goes hand in hand with induction. These are functors, and one is adjoint to the other, like that. It's not a trivial thing, because if you do like categories and stuff, then it's not supposed to work like this, that one tensor functor is adjoint to another tensor functor. Tensor functors are left adjoint to Hom functors, but here these tensor functors are adjoint to one another in this way. Okay. If you like, yeah, we'll just hold on. We'll come to that. Okay, that's one of the great discoveries of Bernstein, is the resolution of that awkward point. There is completing going on. This is in the world of Frechet spaces. Yeah. If you're dealing with p-adic groups, then you don't have to complete. Everything's very algebraic, but here there is some completion going on. And that makes this thing a slightly complicated thing to calculate. Okay. It's not difficult to give an explicit and very concrete description of this tensor product on this board, namely the thing which appears above. On the other hand, if you want to discuss parabolic restriction, this is a more complicated thing. Nevertheless, here it is. This thing exists, okay? And one of the reasons we might be interested in this is that it's related to K-theory. Left adjoints, if a functor is a left adjoint of something else, it maps projectives to projectives. So it's the sort of thing that's sort of a necessary first ingredient if you're trying to understand some K-theory statements, trying to understand the K-theory of some convolution algebra. You want a collection of handy tools which play well with projective modules, and left adjoints too. Okay. Let me just mention a couple of facts. First of all, a wonderful theorem. Oh, here's a definition. I'll do that. I think I mentioned this word last time. A representation of W is said to be cuspidal if, well, I didn't say irreducible, so let's stick it here. W is irreducible. And secondly, all of these restriction functors are zero. For all p, which come from all possible alphas. Okay. There's only actually a finite number of different parabolics out there, because the only thing that's important are the relative orders of alpha 1, alpha 2, alpha 3, those scalars which define the one-parameter group, which defines the parabolic. Okay. Now this space, this module of exponents, has to do with how it encapsulates, in a way that I won't describe, how rapidly the matrix coefficients of W decay to 0. And if all of the exponents are 0, that tells you that the matrix coefficients have to decay to 0 rather quickly enough for the following to be true. This is a theorem of Harish-Chandra that if W is cuspidal in this category of Harish-Chandra of G modules, then W is, in the language of functional analysis, and in the language of operator algebras, square integrable. It belongs to this discrete series that I was talking about. So the discrete series cannot be detected by parabolic restriction in the context of these tempered representations this reciprocity relation means that the discrete series cannot be embedded into parabolically induced representation. If a representation is irreducible and it is not cuspidal, then the meaning of this adjunction relation is that it does embed into a parabolically induced representation. Okay, so it's tautological that a representation is either cuspidal or it fits inside of a parabolically induced representation. It's a theorem which has to do with this dynamical definition of parabolics, that if a representation is cuspidal, then all of its matrix coefficients decay at infinity very quickly, thanks to the reason which connects this to matrix coefficients, and therefore it's square integrable. That's Harish-Chandra's. It's not a big theorem. That's one of Harish-Chandra's theorems. The big theorem is to classify these guys. Okay, I don't want to take up much more of your time, so let's bring this to a conclusion. I need to get the machine here. Let me tell you one more thing, which I think is very interesting from a number of points of view. Helps explain why we might want to have a special emphasis on these cuspidal representations. It also helps explain what the Baum-Kohn conjecture might be saying in the world of representations. It's dry enough. Let's leave it. Okay. I'll just leave it at one theorem. You might ask, well, what about in the S of G, in the non-tempered context? There's another theorem of Castleman which says that no representation is cuspidal. So in the context of general, non-unitary, non-tempered representations, every representation is a sub-representation of a parabolically induced representation. So you know where to look for all of the representations now. It's a pretty cool theorem. Okay, but I'll leave that. And just mention one more theorem, which is an amazing theorem of Bernstein, which you can read about in these notes that I mentioned. But there's a beautiful... This theorem is about 25 years old, something like that. There's a beautiful new account of it. This has now attracted a lot of recent interest thanks to a preprint, maybe it's now a paper, of Bezrikavnikov and Karsten, who reproved Bernstein's theorem geometrically. I'll show you the relevant picture in just a moment. And it's about right adjoints as opposed to left adjoints. And it's in the context of p-adic groups. In the context of p-adic groups, Schwartz functions mean something a little different than they do in the real case, but I won't go into that. In the context of p-adic groups, this guy here is kind of fun, kind of interesting. Oopsie, I screwed up. Trying to fix that. It's about right adjoints, and what Bernstein discovered, it's an amazing thing, is that parabolic induction also does indeed have a right adjoint, but it's slightly funny what it is. It's not the left adjoint, it's this opposite fellow here. This is right adjoint to induction. These are bimodules, and when I say the bimodule is a functor, I mean by tensor product. Okay. So parabolic induction has both a left adjoint, and now we see a right adjoint. So it too maps projective modules to projective modules. And now we have all sorts of projective modules, particularly in the context of p-adic groups, because there's another way of getting projective modules, which is to induce from compact open subgroups. Every p-adic group has lots of compact open subgroups. Induction from a compact open subgroup always maps projectives to projectives, just by some averaging argument. And this Baum-Kohn conjecture is, you can think of it as being about organizing all the projective modules that result. So it has a very interesting representation category theoretic meaning. I won't say anything more than that about it. Instead, I'll show you a picture which is supposed to explain why this is a geometric theorem. Each time you have this categorical relation, an adjunction between two functors, you get what's called a unit and a co-unit. And in particular, you're obliged either to find or to calculate from the adjunction such a bimodule map as this. This is called the co-unit of the adjunction. So the proof of the adjunction relation will give you some canonical bimodule homomorphism like this. And it's kind of fun to see what it is. And it has to do with dynamics. It has to do with the shape of G mod n and something slightly more complicated than G mod n. Okay, that was a fail. So I have a current favorite picture. It's not a triangulation of the Poincare disk, although the Poincare disk is in the picture, but it comes in a little slightly differently, which I'll end with. So let's see what it is we're supposed to do. You can calculate what this tensor product is. It's rather easy because L is acting properly on this product of G mod n times n bar mod G. This is the same thing as the following space.
I realize that I'm confused with you, right? S and G is right because you have to maybe tell us the tensor product is over.
Yeah. It's over this convolution algebra S of L. Yeah. So the left coset space has a right action of L, and the right coset space has a left action of L. So this thing, the left factor is a right S of L bimodule, and the right factor is a left S of L bimodule. So I have all of the ingredients I need to form this balanced tensor product. Yeah, yeah. Right, so what I'm saying is that if you have an adjunction, the category theorists tell us that if you have an adjunction, it's some natural isomorphism, as you know, then associated to that adjunction are two canonical natural transformations, the unit and the co-unit. And this is the manifestation of the co-unit of the adjunction. This pops out of what it means to be an adjunction, which I did not tell you about because, well, I'm just not going to tell you about it. But what you get is a very interesting transform of functions. There should be some canonical bimodule map from functions on this space to functions on this space. And now let me tell you what these spaces are. It's kind of fun. Let G be SL2 of some field F. It could be the real numbers, and it could be the p-adic numbers, but I'll draw a real picture. We're not equipped in this facility with p-adic blackboards. We're also not equipped with three-dimensional blackboards due to budget cuts, and so I will draw a three-dimensional picture of these, of what should be a four-dimensional space. So here's a cone. Okay, in this cone, you're supposed to think of this as a set of all 2x2 matrices. So it's a picture in R4, not in R3, or F4, not in F3, and it's the picture where the determinant is equal to 0. On the other hand, if you ask what about the SL2, it sits inside of R4. There's, of course, the set of all points where the determinant is 1. And there's a one-parameter family of spaces in between. Okay, and this thing here, this cone, apart from the 0 guy, is exactly this Bernstein space. In the case of SL2. So I'm trying to build a transform from functions on this space here, which is the cone, to functions on the hyperboloid. And if I'm talking about p-adic functions on complex functions on a p-adic group, I'm talking about locally constant functions on the cone. I want to move a function which is locally constant on the cone over to a function which is locally constant on the hyperboloid. Well, they're locally constant, so as long as we go far enough out to infinity, where the distance between the hyperboloid and the cone gets really, really small, there's going to be a canonical extension just by local constantness. You extend as a locally constant function, and if you think about it, that makes sense. It gives you a well-defined, so to speak, asymptotic map from here to here, and then Bester, Kapnikov, and Kashtan argue that this asymptotic map has a unique extension to an actual map. Okay? But it's very interesting now to ask what happens in the real case, and let me just tell you about that. Okay. Oh, first of all, here's another theorem. I won't tell you about that, because that's too much. I'll just end with one statement. The same is true for real groups. Not all the time, but in the tempered categories. This is definitely a false theorem. This second adjoint theorem is false for the Schwartz algebras in the real case, but it's true. It becomes true again. It's kind of amazing in these tempered, in other words, these Harshchandra categories. And then it's a very interesting business to try and figure out how to build a transform. I'm telling you that there's a canonical way of transforming functions on a cone. This is the cone inside of R4, defined by this equation. There's a canonical way of transforming functions. It's completely G by G equivariant to get a function on the cone and push it onto the hyperboloid. It's not obvious what that is. It's the solution of a dynamical problem. It involves the wave equation. So it's wave dynamics, not point dynamics, if you like, which becomes very significant in understanding what's going on here. Anyway, we have lots of adjunctions now, lots of ways of manipulating projective modules, lots of tools that we might attempt now to apply to K-theory, or L-theory, in order to understand what Baum-Kahn is saying in a way that's more closely related to representation theory. I think that's enough. Thanks.